Okay, perfect. Thank you all for being here. Good morning. And so we are going to have a talk by Carson here. You know him, so I don't have to introduce him that much. Hello. And he's our PhD candidate here at the FISC. And he's going to talk to you about a new nice library that he has been developing. So without further ado, the floor is yours.
Thanks for the introduction. Exactly, we'll introduce the new library infomeasure today. It will be a talk about chess, about brain dynamics, about many more things, but most importantly about software and information theoretic measures and estimators. This work has been in work for like around about a year, and yeah, I have been collaborating with Kishore Acharya and with Massimiliano. So, next slide. Just quickly, what we'll go through. First, I'll explain you a bit about the background. What was our motivation of starting a new code library again. Then we'll show you some demos. That's the most important. And show you a bit about the time complexity, about the time our code runs and how quick it is. Let's start with the background. So information theoretic measures have been applied in a wide amount of fields. It starts at the small parts that make up our bodies in biology, as example for molecules. In complex system analysis, you have surely seen in the most basic course entropy as a measure introduced. Through physics, finance, when you want to look at information shared between stocks as example, but also ecology, COVID as example, neuroscience, brain dynamics, we'll have an example from that today as well. But also really important in machine learning and the large language models like we use in ChatGPT and so on. Cross entropy is plays a really important role. And another field these measures play a part in is outer space research. And of course, this list is not extensive, but just to give you an idea. So we first wanted to identify the barriers of applied information theory, because we as scientists, usually we also apply our theories. We're going to go from data to an output, a number, when we have not just theoretic data. So the first challenge is the estimation challenge, because the measures are usually defined with probability distributions, but in the real world we need to measure the problem. We need to measure anything what you want to talk about, and then this additional problem comes into place. We need to approximate the probability distribution to actually get an output of the measure. And this can also introduce biases. I will talk about that in a moment. Furthermore, there is a huge software fragmentation in the space of information measure libraries, which introduces more problems. As example, the maintainment software evolves, but sometimes the software we wrote 10 years ago doesn't work anymore with what you have, what you got today with the. Let's say Python evolves, but your software is old and then it doesn't work anymore. But also, when we have many different implementations, one scientist, one software engineer might say, okay, my 0 is this, but the next one, his 0 is a 1. And another nice thing is, well, not so nice thing is, there are often self-made solutions when you are, let's say, a master student and you get a task. Okay, you should implement this, which is good to understand something. But when you want to publish something, it's good to have clean code. And yeah. Furthermore, there's a third barrier, the reproducibility issues, which stem from the one before. The differences on the implementations, on the definitions, and so on. And often there are details missing in articles about how you have gotten to your result. And lastly, there are computational barriers. When we want to reduce the errors and biases, often we need a large data set, maybe not too large, but at certain scales, the computational cost, well, scales with it, or often even scales with it quite non-linearly. And because of that, we need to have robust and optimized algorithms that are also user-friendly. So the package works as intended. To shine a light on the the first challenge, the estimation challenge, this is, I want to really emphasize that often forgotten but crucial step. You say, okay, we want to measure, we have this problem, and now we want to calculate the output. But then when you start the measurements, you notice, oh, okay, but what is this distribution? And suddenly you have this problem you didn't really think about before. And I mean, if you have done it more often, you know that this is really important, because depending on how you assume your probability is looking like, or how you estimate your probability distribution, you might capture different aspects of the data. You might introduce or minimize certain biases and errors. And another key aspect is also the efficiency and accuracy you get from that, because one approach might be much quicker than another one, and then depends what you really want for your research. Just to show you the software fragmentation, we just found these how many? 10 different libraries, and surely there are more. And all of these libraries, they focus on only different specific methods or information measures. As example, some of these are only discrete, and there's one that only can only handle ones and zeros in data. And then there is another info theory library which can also handle this continuous data, but the estimating approaches are quite limited. And then on the right side, you see the DIT package was updated in April. The most recent one, which was updated, is the Java one, but it can also happen that you have one which has not been updated for like 10 years or more than that. And then do you still want to use the code or not? So this is the problem which we want to solve with our infomeasure package. So the vision is we want to unify approaches and measures to have a comprehensive, consistent, and user-friendly toolbox. The core principles, I will just tell you about some of these, are that we, like I just said, unify the approaches and standardize a way of working with them. Of course, we want to have implement the state-of-the-art estimation techniques. We want to have the most important ones. And we also want to enable local measures, p-values and t-scores. To some of you, this might not, well, local measures as example might not be a topic, but to some of you, it might be interesting. This is important when you have time series and you want to see in what part of the time we have a certain information, as example for mutual information or for transfer entropy. That's really interesting. But also for networks and building up networks, the p-values and t-scores, they are quite valuable, let's say. And yeah, with this, and as motivated as before, we want to also maximize reproducibility through these approaches. And we also want to ensure computational efficiency of implementing quick algorithms and also optimizing them while conserving the accuracy and numeric accuracy. So big table, I'll give you a moment to see. So on the left side, we have the different measures which we implement, quite wild and varied, but the most standard measures. So it goes from entropy, not only Shannon entropy, but also Renyi and Salas entropies. over to joint entropy, cross entropy, mutual information, conditional mutual information, transfer entropy, conditional transfer entropy, Kullback-Leibler divergence, Jensen-Shannon divergence, and also for Renyi and Salis, most of them again. And these are all paired with these different estimation techniques. So the most classic, of course, would be the Shannon entropy for discrete data. Most important, is super quick, but if you have continuous data, you will not get far with that. I mean, you can discretize your data, but your output can be better with, as example, if you use a kernel estimator for continuous data or a metric KNN estimator. And furthermore, we also have the ordinal estimation. This is important when you have permutational patterns. So you see, we kind of match nearly all measures with all estimation techniques. And this table is, of course, well, for now, this is the most important, this as we have, but it can also be extended in the future. Exactly. So the architecture, I need to mention this because this talk is kind of also about that, but don't worry if you get lost in these 2-3 slides. Later on, we'll catch you will catch up again. So the core components of the infomeasure library should be a modular design. That means we can extend it later. We want to use inheritance. That means we only want to implement certain things once and then reuse that again, because we do it really good once. If we notice an error in here, we can correct it in here, but we don't need to refactor the whole code base. Another thing maybe that we can highlight is the dynamic import mechanism for memory efficiency. Sometimes, well, you see that we have quite many approaches and measures. And if you only use the ordinal ones, let's say, we only want to import into the kernel the ordinal dependencies and only our ordinal approaches. So that means that if you import the whole module, it will just take a moment. And if you use a certain part, it will get that into the kernel, but it will not bulk up your kernel. Right. So as an example, this is the entropy for the entropy, the inheritance diagram. We have a class which is the estimator. And this is an abstract base class. And all of the estimators inherit from the estimator through the entropy estimation. This is important because in that way, all of these estimators, you can talk to the same way. When you program and you want to switch from the Renyi entropy estimator to, let's say, the discrete entropy estimator, you just need to switch the approach and the rest works the same. Of course, there might be some parameters that you need to change and also maybe switch to discrete data. But this reduces your work in the end. The same, or well, also inheritance diagram we have for the mutual information. Here we have some more because we don't just have the normal one, but also the conditionalized versions. And here we also introduce the p-values. And then for transfer entropy, it's kind of similar. The whole package looks like this, but you don't really need to understand this. What you need to understand is pip install infomeasure, and then you have it for Python. I haven't mentioned that, but it was in the title. I guess you've read that. You just install it via pip, and then you wait a few moments. If you don't want to wait so many moments, you can also use Conda or Mamba. Then it's installed much quicker. And the usage, you only need one line to get any measure. Entropy, you get like this. You import the package first, of course. You put in your data, time series data. Doesn't need to be time for entropy, but write your data points. Then you say what approach. In this case, we want to have the kernel approach, a certain bandwidth, a certain kernel. We could also say we want a Gaussian kernel, but the box kernel is much quicker and the performance is kind of similar. And we get the entropy. If you have 2 data sets, or well, a data set of two time series and you want to find out what the mutual information between these two is, you have another one-liner. And let's say you want to have the discrete one. For transfer entropy, same game, source, test, variables, two random variables. In this case, we can have the metric approach, and we can also introduce some noise, which is kind of useful for this. It's a standard for the metric approach, for the k nearest neighbor one. And for mutual information and transfer entropy, you can also, like we shown before, add a conditional variable that would just be another variable here. Okay, let's go a bit further into the demos. And for that, I will sit down because it's a demo, you know. We actually want to do it live. So we import the infomeasure library, a plotting library, and NumPy. And of course, we need to set our number generator. And let's say we start with a normal distribution, because for that we can have we do have the analytical output for entropy. So we generate 200 data points. Then we can look at the data. So we have one example time series here for a certain standard deviation. And the histogram looks like this for different standard deviations. I think I already, yes. We can calculate the analytical entropy. And now we want to calculate the entropy for all these different approaches with these parameters. And then we get a plot that looks like this. All except the ordinal approach have roundabout the curve of the analytical result. The ordinal one does not, well, it's constant because it is only sensitive to the amplitude, so we expect it to be flat. But let's just use a bit more data points. Let's crank it up 100 times. We see our histogram is much rounder. Calculate, done. And we see the curves fit much more on the analytical outcome. The discrete one is a little bit lower here because of the discretization we do, but that's fine. Another demo for the mutual information. There we have the multivariate normal distribution with that covariance matrix. And we also have an analytical outcome for the Shannon entropy. So we have something to compare it to. We generate 200 data points again, so we can have more later. And this is the joint distribution. So you see in yellow, the correlation coefficient is higher than the one for the dark blue ones. So these yellow ones kind of form a line, and the other one are just splattered around, kind of uncorrelated. And we calculate the mutual information here, just this line, and plot the whole thing. And we see in black the correlation, mutual information by the correlation coefficient should be increasing, and the trend is in all of the curves, but we lack some data, but we can't just get a little bit more data because it's generated data. Let's do 2000 first. So we have a little bit more data and already see the most of the approaches got a bit closer to our analytical output. Let's be a bit crazy and turn the data up a little bit more. Now calculate the mutual information, done. And that looks much better, right? I mean, it's synthetic data, but this is the validation. We want to know that our code is behaving well. Only Salis is still with an offset, and that's fine because Salis here has the Q parameter not equal to 1. Only for 1, it would be Shannon entropy. So if we put it to 1, it also matches. Okay, now let's have 2 more or three more interesting it's just toy data examples. Let's say you have three players with a Pokédex and you want to know what is the surprise, what Pokemon your opponent might get. And you see we have these three players, and for the last player, the surprise, the entropy is kind of more low. And this is because this player will quite probably play an Onyx, because it's an Onyx nerd, I guess. Just one quick example. And you can also have an example of film data, which you get from the internet. These are movie ratings by year with name, and also important, the profit and the genre of 1,759 movies. And we can look at the distribution. So here we have the frequency of the profit. So you see some movies have a quite like much higher profit, in order of magnitudes higher profit than other movies. And the whole entropy of this data set is 19 if we use a metric approach. And wanting to look into the different genres, we can look what the entropy of the different genres is. And here we have outputs of, well, entropies of around about 18.4, I think is the most small, to 20 point something. Now one could say, okay, if I want to have a movie that has a profit margin with a certain entropy, I might switch, go to, let's say, the TV movie to have a lower entropy of profit. But I mean, roundabout they're kind of similar. So if you produce a movie, it doesn't really matter the profit entropy there. But just as an example, and to get a little bit more real data, well, this is also real data, but more current data, we can get the last 500 games of the player David OR 2899. This Berserk package is connected to the Lichess database, which is an app, online app of chess, where there are many players playing chess on their mobile phones, on their computers, and it is quite nice place to get data. So what we can look at, what we just now downloaded, are the last 500 games from October till yesterday, of this one player, and each game has a string of moves. And to do a short pre-processing, we can remove the checks of this and then look at the entropy of all these moves for each game. And then we see for each game we can get an entropy of moves. And here maybe we see what's interesting. This is a distribution which is unsymmetric. We can also look at that in a histogram. So the entropy goes from just below 2.5 to just below 5 if we use the discrete approach, because a move is a discrete thing. You do it or you don't. You can't just put your chess piece between the fields. And maybe one thing that might be interesting here, for these 20 games, the entropy was a bit lower, but it's still it's not really insignificant, but maybe at that point in time, that player has played always the same thing, or well, a certain, well, less entropy in their moves. But to finish this example, we can look at the entropy of the moves per game by the number of moves until the game finishes. And here we have the scatter plot of all these games. In black, a fit of a logarithmic model, and in red, the upper limit. The upper limit is if in each game of this certain length, the player plays one move only once, at least in the notation. So, I mean, you can get into really many details, but this is just a toy model to show you what you can do. And this example we did yesterday with that player, that might be here in this room right now in just like half an hour. So the most important thing is like the most code, and what you see is just getting the plots together. But it's always just one line, getting entropy, getting any measure. We also wanted to reproduce a paper. Let's get back to presenting. A paper which has been quite important, a seminal paper from Schreiber. These are two plots from the original paper of transfer entropy and mutual information of tent maps and coupled Ulam maps. And we were able to reproduce them with our package and also do this fit. If you want to know more about this example, you can look into the documentation. We have written down all of the details for this one example, but we also have the Gaussian data here and also the time performance, which we'll show in a moment. But to move to another one example, I would hand over to collaborator Massimiliano.
Okay, thank you. Just to intervene a little bit here. So another example that we wanted to try to test is the analysis of brain activity, especially because this kind of measure, transfer entropy and so forth, have been used a lot to understand how information moves in the brain. This is something, of course, that we would like to see in the sense that we want to know how the brain works during a task or during a resting state or whatever. But the problem is that, you know, you cannot easily open a brain and see how the information moves there. I don't know why, but control subjects don't like that to be done to them. So it's difficult to get volunteers. So what we usually do is to reconstruct functional networks of the movement of information in the brain, which entails recording the brain activity at different places through electrodes, for instance, electroencephalography electrodes that you put on the scalp. You record the brain activity, then you have time series, and then you try to understand whether there was a transfer of information between the activity of different sensors, or more generally, a correlation or a synchronization. Assuming that if you see that two brain regions are correlated or are synchronized, it means that they are sharing information somehow between them, and therefore that there was a transfer of information. This is quite, I mean, this can be discussed. It's not that simple, but this is what it has been done in neuroscience. So we did something similar. We took a data set that is open. You can download it. It's quite nice, quite clean. You have 14 recordings of schizophrenic patients, 14 control subjects, and you have 19 electrodes and a resting state, quite a long resting state. So the subject was just laying there doing nothing, and the activity of the brain was recorded. And our idea in the next slide, you can see that we calculated the transfer entropy across all the possible pairs of electrodes that you have, and then we calculated the average, and this is just for control subjects. But the point is that in many cases, you look at the papers that have been published and they say, yeah, we have used transfer entropy. Yeah, what estimator? Because there are many estimators. Which one? We tried the three: box kernel, KSG, and ordinal, with the idea of, let's see if they give the same or there are differences between them. Well, here you can see that, okay, there are some mild differences. Just to be clear, black colors indicate that there was no transfer of information between a pair of electrodes in the brain. And the bright colors, it means that there was a very strong transfer of information. You can see that there are some differences that are not very clear. It seems that the ordinal pattern has more transfer around the temporal lobe. Here, the box kernel is more in the frontal, more or less. Okay, this seems okay. There are some differences between them. Why should we care? Well, we should care because then you look at the difference between control subjects and patients, because at the end you want to know why patients are different. What is their brain doing that a control subject is not doing? So we plotted the difference. In red, it means that the transfer entropy was lower in patients, and in green is that it was higher in patients. So green means that there was a stronger transfer of information between these two parts of the brain. And you can see some quite weird or wild differences between the three estimators. So they are all normalized according to the same scale. So the color represents the same intensity. And you can see that according to KSG, there are essentially no differences between control subject and patient. There are actually some differences, but they are so small that you cannot see the difference in the graph because the colors are not, they don't have enough resolution. According to the box kernel, there are also some differences. You can see some red, some green, but the point is that it's there is no structure there. So it seems that the differences are quite scattered across the whole brain. On the other hand, you look at the ordinal pattern method and it's like, okay, quite clear, right? Everything is green. So according to this method, patients have a much higher transfer entropy across the whole like connectivity range than control subjects. So it's quite important. One of the advantages of this library is exactly that we did this, and it was exactly 3 lines of code to change between the 3. So with 3 lines of code, you can do all this analysis, and it's very nice because then you can compare them and you can choose the one that is better for you. Of course, then you have 100 line of code to preprocess the data and all of that, but that's another story that has nothing to do with the library. Okay, thank you. Back to you.
Thank you. So that was the last example. And just to wrap up, we wanted to compare the time complexity because if you have a larger data set, we also still want the approaches to work out. So here we plotted the time of execution for entropy, for mutual information, and TE for the different approaches we have, also with different parameters, by the data length. So what if you put input roundabout data of 10 samples to 10 to the 7 length of data samples. So here for MI and TE, we have either two of these data input lengths. And to summarize these 3 plots in one, you can always process these measures for all of these approaches and for all of these measures in if you have 10,000 data points in less than a minute. And so the worst performance is always the kernel approach with the Gaussian kernel. You see the red is always scaling the highest. But if you still want to use the kernel approach with a quicker kernel, you can just use the box kernel and you already save some, let's say here, 2 orders of magnitude around 10 to the 5 for entropy, but also there. And what we also can see is the discrete approach of discrete data is the blue one, and it always outperforms the other approaches. Yeah, and just to note, maybe you already thought about that, in the usual case, we don't have as much data. So the performance is good and it does not scale too bad. And well, one last thing, usually when you have the ordinal, the permutation approach, and you have the one most important parameter, D, the embedding distance, the pattern length you are looking at. The most important is, well, the most used one pattern lengths are 2, 3, and 4, but many people don't even go higher. But if you want to have longer patterns, the space of possibilities just explodes by, I think it is factorial. So when you try to increase that, the performance just breaks. But in our case, we implemented in a different vectorized way. And you can see that the embedding dimension for the ordinal approach for D equals 3 and D equals 8 is kind of matching. So here the purple is just below the brown data points here. And here you see they are on top of each other. So this is another nice thing where you can compare to a quite long embedding depth. And wrapping up, let's get back to our 4 barriers of applied information theory. Did we arrive at what we wanted to do? So first, estimation challenge. You've seen we have a wide variety of estimators for all of the different information theoretic measures. And we have always one consistent interface, which allows comparison between the different methods. We also try to combat the software fragmentation by just building one package, which supports most approaches, as you've seen in the table. And the third, the reproducibility issues are also now minimized. So we've done our part. Now, if you want to use the code and you want to publish, just share your parameters and tell that you used our code. And then it's really easy to reproduce your output if you also make your data public. And lastly, the computational barriers have been battled by optimizing the code, as you've seen before, that the computation does not explode even worse. So, yep. And to put it into a picture, the workflow before was usually you have a question and you need multiple libraries, or you build your own code, you integrate everything together and you get your result. And now we just have question, infomeasure, result, and also the plotting and so on. But the output, the data you get in a really short step. And yeah, to finish, if you want to learn more, you can find the reference guide online. You just need to search infomeasure and you find it. You can also, in a few days, I think, read our preprint, because it has been on hold for like a week on the archive. The source code is also available if you really want to read the source code. It's well documented. It has comments. So usually it's just like so much comments and then the code. And the version on Zenodo. And you can also find these presentation slides online, which are also linked in the last invitation we sent out. So there you can find these slides with this notebook. And yes, so if you want to start using infomeasure, you install infomeasure with pip or mamba, and feel free to contact us, to contact me if you have any problem, any suggestion. You can maybe think now, where can I use this package? Or come up with another improvement of the chess example, how you would do it, and let us know, or just publish it. And yeah, if you find an issue in the code, just email me or report it on GitHub. Of course, our code has been improved and has been worked on for a long time. We have tested it, we have validated it. You will find that in the paper. But perfect. What is perfect? We also always need to be the best version of ourselves. And of course, we also need to acknowledge the funding. And then finally, we're thanking you for your time. And yeah, thank you for listening. I think we can finish the recording and then go into questions if you want.
Okay, thank you.